HABCO, and we're building an RFID tool tag machine for them. My name is Ryan Mannix.
I'm Joe Joaquin.
And our HABCO contacts is Peter Green and David Pliss, and our advisor is BZ. Our main objective is simply to build a milling machine that mills 60 thousandths of an inch holes into 3/8 inch sockets for HABCO in order for them to supply to aerospace industry foreign object damage reduction. This simply just allows any aerospace industry to reduce the possibility of leaving a tool out in their workshop and possibly leave it in the engine and create damage in the actual engine. And they do this by simply using a library system of a workshop bench that basically uses an RFID tag to know if the part is in there or not in there, and they check it in and out, and they know where all their tools are at all times. And this is the size of an RFID tag.
So to start off with preliminary testing, we performed a non-scientific, no data was collection sanity test at the SCA shop in the mill. And you remember last time we were worried about the chrome coating of the sockets? We were afraid that the end mills have a lot of trouble getting through the chrome coating. It turns out it was not an issue whatsoever. We performed both side milling and plunge cutting into the sockets. Left the coating, no issue. Just from the feel of the machine, the vibration, we determined that side milling was better than plunge cutting. Plunge cutting was harder on the machine, harder on the socket, harder on the end mill. So we just kept this in the back of our mind, moved on with testing. So our first official test was in the Yukon machine shop. We did it on the Bridgeport mill. And our purpose was to decide between plunge cutting or side milling, also to decide our end mill and the ideal feeds and speeds for our process. So what we did is we clamped our socket into the vise. We used different 2-flute or 4-flute end mill and performed our testing. The result of this testing was we determined that side milling is the best process for our machine. On plunge cutting, as you can see in the top right corner, at the very bottom of the, we chipped the tooth in the first cut plunge cutting with our 2-flute end mill. This would not hold up for tool life. So we decided to go with the 4-flute. It performed flawlessly, 20 plus cuts, no issue, no damage whatsoever. Through the testing, we determined that side milling was the best. Of course, we did the damage for plunge cutting. With the parameters, we determined that 20 inches per minute and 2,500 RPM was the ideal feeds and speeds for our cutting. The only issue with this cutting is we noticed that the surface finish on the cuts was very smooth, which is not what HABCO wants. They want to have a roughened surface to glue the RFID tags down to. We were getting a close to flawless finish, which is usually what you do want, but not in our case.
So you may be asking yourself, how did we come up with 20 inches a minute? Well, this is our calculations that we had. We had lots of variables coming into this project. We needed to know what end mill to use, how much material, the amount of material we need to remove proper, the speed. So talking with HABCO, we decided that we were going to experiment with one of their mini millers that they had picked up. It has a 4/5 horsepower spindle and a maximum speed of 2,500 RPM. Using this, we were able to calculate our spindle power, knowing the efficiency is about 90% of a direct drive belt system. So using that and knowing that we have a spindle speed of 2,500 RPMs, we could calculate our material removal rate, knowing the size of the slot we're milling, the socket we're using, and that comes out to about 4.45 cubic inches per minute. Now, in industry, it's a standard with the hardness of our socket that we're using. It's about 1 horsepower per 1 cubic inch per minute of material removal. So just as a sanity check, we made sure that our spindle, using the spindle, would be powerful enough, and it actually was. It was about 40% more power than required. And now that we knew that the spindle had the proper power, we can go ahead and calculate the inches per minute, knowing our maximum RPM of 2,500 and knowing the number of flutes and the inch per tooth. On our end mills, we calculated about 20 inches per minute. And just for a check to make sure that our end mills would last while running them, we calculated the surface feet per minute. It was about 245 surface feet per minute, and the industry that creates the end mills said that it should be between 200 and 400 to get maximum life out of the end mill. Now, we had the issue with the surface roughness, or lack of surface roughness. So in conjunction with Habco, we developed the second pass technique. If you look to the right, you'll see that an end mill is actually not flat in the bottom, and ours had a 5,000 step. So we use this to our advantage. Our first pass would be at 55 thousandths, which is 5 thousandths less than the maximum depth. And we would come back with a second pass, about 5 times the speed of a normal cut, about 100 inches per minute, leaving scalloped grooves in the bottom of the end mill. This was done as an official second test in the Yukon machine shop on the Tormach CNC. This provided a rougher surface finish, which is more to what Habco was interested in. And if you look on the top right, you'll see the surface finish is much more coarse than just the first testing. And on the optical comparator, you see that there's the scalp marks. And we also have a quick video to show you the process and what it looks like. So the machine comes down, does its first pass at 20 inches per minute, drops back down to 5,000 deeper, and then comes back at about 5 times as fast, leaving our scalloped edges that we were looking at.
Our third and last testing of the semester was testing the cutting forces on it. We went into the machine lab and used a force transducer as well as this V-block or custom-made V-block that we made and measured the X, Y, and Z cutting forces. And this helps us to design the pneumatics for our machine, as well as allows us to do further analysis and ANSYS or moving forward with these forces. The results that we got are, we got a maximum peak cutting force of 55 pounds over here. This is on our primary cutting pass. And then on the secondary pass, we had a force of about 20, a little bit less, around 18 or so. And you can also see the amount of time it takes to cut. It's 0.5 to around 2.5. It's 2 seconds of cutting. That's very fast, plus just generating really fast cutting speeds, allowing a lot of sockets per minute coming out of the machine.
We have machine design. So we've purchased, or Habco has purchased the mini milling machine for us. We're going to fold it apart and use the spindle for our advantage. Finding a spindle was pretty difficult until they came up with this idea. Also, we were going to take the bottom table off and use that as a part of our machine. So we performed the testing at Habco, and we found that the machine actually was powerful enough, and that our theoretical calculations did meet up with our with the real world. And we were going to use this idea to build the custom fixture for the sockets, and then automate the whole system with the PLC logic controller. So this is the quick sketch of our machine design. We had another one, but we decided that this was the way to go. If you'll look on the, if you'll look right here, you have the spindle laying. This is the top view, and you're looking down on it. The spindle stays stationary while the table will be moving. We have a V-block that comes in and clamps the socket against the fixture plate. The end mill sticks through the fixture plate, and then the table moves after you hit the go button. After the first pass is done, it hits a limit switch. The machine knows this, and then reverses back at 5 times as quickly until the second limit switch is touched and the machine is turned off. This is the front view of the plate where the end mill sticks through and it cuts across the socket and then back again. This is the machine taking delivery, sitting in Castleman.
This is the PLC diagram of it. This is a more logic-based breakdown of what Joe just said. Basically, we're going to be using electronic and pneumatic force inputs into the machine, and there's going to be multiple inputs and outputs. For the inputs, there's going to be obviously the start button, the 2 limit switches, so we know where it is. It's going to be starting position or ending position, or it's a stop and turn around. And then it also has the emergency stop button. The outputs that we're going to have is once it hits start, then you have to clamp the vise that actually holds the socket, and then it also has the push and pull spindle forward going either the 55 thousandths of an inch first pass, and then the 60 thousandths of an inch second pass. And then it's going to have 2 different table speeds inputs that will have to vary. And this is just a diagram to show the actual logic taking place. You hit the start button, then the V-block clamps itself, the spindle starts, the spindle is then ordered to be pulled back to the 55 inches or 55 thousandths of an inch, and then it's going to be jogged at 20 inches per minute and cut across the socket, and it's going to hit the first limit switch, and then it's going to stop the table, and it's going to push the spindle forward the extra 5 to make it the full 60 thousandths of an inch, and then it's going to run it itself back at 100 inches per minute, and it's going to hit the second limit switch, and it's going to stop the table, stop the spindle, and unclamp the socket, and the user can take that out and input the second one and just keep running. And this total time should be very quick and should generate many sockets in under a minute.
So moving on with the budget, we already received our bill, it's $500. We're looking at device materials, miscellaneous hardware, another 150 about. On the controller, we've been looking at controllers. There's a lot of information to take in. We've been calling companies, trying to figure out which one's the best for our application. So until we decided on the perfect controller, we took the average, about $300 range for a controller. Same with the drive motor, we've been looking at AC motors, DC motors, motors with feedback like servos or no feedback, just a standard electric motor. So we get the average $150. Everything else, electronics, travel switches, wiring, the pneumatics, all adds up to about $1,500 in the end. Still a rough estimate, can go up or down depending on the controller or drive motor that we decide upon. And continuing with the timeline, we are still on schedule. We're doing final design reviews with Habco. Have been working more of our 3D modeling since we just got our mill, or we just began 3D modeling. We're going to do design reviews with them, make sure everybody's on the same page. Then we're going to order materials before winter break that we had planned, and continue and start building the machine. So, in the next 45 days, we will, like I said, final machine design, work more on the PLC final design. We got a good layout. It's just getting which sensors we need, everything we're going to need for that. Full CAD model, like I said, order materials before break, all the PLC components, the fixture, and the mill modifications. We're going to be modifying the mill very significantly. Any questions?
Any questions from the audience? I think I remember last time you had a mark of like 100 tools per end mill.
Yes.
How do you think you're going to come in above that mark?
I think we probably will. We've done, so our first 4-flute end mill, we did about 20 to 25 cuts on it, and then we tested it at Habco. We ended up breaking it because on this machine, the vise and fix and the table, they're a little loose, so it's bouncing back and forth a lot. I think that's what broke the end mill. So we just received a new end mill. We've done another, say, 20 or so cuts on it. Still looks brand new.
Okay.
Life testing is still to come, but we do want to get force testing, all this stuff done beforehand because that's really more important